Well, I reread crystal radio sets, the simple cat whisker kind. I had to find an article that actually explained what the purpose of the diode was for. And they used an analogy, which basically, what I got out of the analogy was that it has to do with phase lock, because they gave the analogy of a pebble falling into a pool of water creating ripples, and everything is nice and neat and tidy. But you throw two stones in the pool of water and it gets messy, and some of the waves cancel each other out. So the diode is used to cancel out waves part ways so that you don't get cancellation of the waves. I think you cancel out the second half of the waves. Anyway, regardless, what I deduced from that is that it's a phase lock problem. The waves have to be in step and not out of phase, or else you wouldn't get a clear audio signal. And I've already done that by taking multiple capacitors and interleaving them. That's when you put the first plate and then you put a floating plate in between, because if you assume an AC signal, which is apparently what a crystal radio does, it assumes that's what it's going to get. It's going to be a wave going back and forth. And so the diode is there is to cut out half of that motion so that the wave that gets through is only shaking in one direction. But so if you have an AC input and you have multiple capacitors that are interleaved, you need an odd number of plates to create the right polarity when you interleave them, because you take two here and you take two over here, shift it over one notch, and when you draw a plan assuming positive on one lead and negative on the other during any half cycle of the AC cycle, the plates don't match up, the polarity, and so in order to get them to match up and not conflict, you have to put in a floating plate. So during any half cycle you have a slightly more than 50% charge of plates dominating. In other words, if you had two capacitors interleaved with one floating plate, you'd have 5 plates. So during one half cycle, you'd have 3 plates negative and 2 positive, and then the next half cycle, it would invert itself, and you'd have 3 negative and 2 positive. Did I say that right? 3 negative, 2 positive, 3 positive, 2 negative. And it would go back and forth, so it'll always dominate. It'll never be balanced. It'll always dominate in one polarity, which is kind of interesting because that's what over-unity devices usually rely on, is asymmetry. So the device may be amplified. Oh, well, the diode is actually meant to clarify the signal, or does it amplify it? That's right, it amplifies it in the sense that it prevents cancellation from occurring. So phase lock, meaning resulting from interleaved capacitors, I think it does the same thing. It eliminates the disorderliness. It improves coherence among the waves, and you don't need a diode. You still retain the AC character. You don't filter anything out, I don't think. Well, maybe you do. Or do you put a time lag on it? Maybe that's it. Because all the plates have to charge and discharge at the same time. So you have to wait for the waves to catch up? I don't know. That's interesting. It's one thing I don't know, because I got the idea from a person who wrote a page on the Jean Naudin website in France, I think it is. And I derived it from his idea. I think I modified it slightly, maybe. I can't remember. But that's where I got the idea from, and I didn't know what it meant, phase lock, until Eric Dollard had a discussion with Aaron Murakami, and then I understood, oh, phase lock. That's what I did with the interleaved capacitors. So it doesn't need a diode, and that's interesting. It's very interesting. So, okay. Then I don't know what step to take next then. I haven't the faintest clue. Right. Okay.